Rutherford only has done the experiment. He has taken the alpha particle somewhere, say we are having the alpha particle. We know that charge of the alpha particle is 2 times of that of proton, right? Alpha particle charge is 2 times of that of the proton. That you must know. Now, this is being projected. Projected means we'll have certain velocity here, right? We'll have certain velocity. So it will have certain kinetic energy. If it is being projected by V and then this fellow is moving towards the right means we are having the here somewhere the nucleus from where it is coming back. And then from that, we are able to understand the size of the nucleus. How come? We'll discuss. So say this material, we can take anything, any material. So this material will have the positive charge and we'll call this that positive charge as Z into E. E is the basic charge, we call that of the proton is the basic charge that, you know, this is your 1.6 into 10 raised to minus 19 coulomb. So Z multiplied that. Z is the constant, just number. So material to material, this Z will vary. So proton resides inside the nucleus and proton charge, each proton is having charge E, basic charge E, and there are Z into E means there are Z protons, Z number of protons inside the nucleus. That way you can understand, you can signify the meaning of Z here. Right, and that again, material to material, of course, the Z will vary and accordingly positive charge contained by the nucleus will vary. So now this these alpha particle is able to reach up to that point maximum and then it is going to come back. There is a U-turn here. It is not entering further. Means, okay, it is up to us. More the velocity, more closer it will go. And then we are looking for the closest distance. There is a meaning of that. We should discuss that. There is a concept, closest approach, closest distance. So this closest distance is the distance from the center of the nucleus up to which the alpha particle can go. Up to that, the force of repulsion, because it is coming back with the help of force of repulsion because of the force of repulsion by Coulomb's law, well set in Coulomb's law. If it is going in that, you know, inside that nucleus, the moment it enters, cross that boundary, it will never come back. Even if it is, you have projected with the more speed such that it is crossing that boundary, it will never come back. Reason behind, the moment it enters that region, it will be very, very close to the center, or means it is inside the nucleus. The particle which has gone inside the nucleus experience nuclear forces, right? They will experience nuclear forces. These nuclear forces are always attractive in nature. Got it? Even if we are having like, and this is the reason why this, you can ask that, oh, there are so many proton inside the nucleus. They are all positive. Why not they repel and come out of it, right? Because of the nuclear forces, which is nature is positive, this proton and proton, okay, that is the positive charge, but here Coulomb's law will fail and only one force will act, that is your nuclear forces. Nature is attractive. So I'm talking about that velocity of the alpha particle once it is projected from a certain distance from the coil or the nucleus, now we can say, you know, that velocity we are talking, with that, it can come back. If it is more than, slightly more than that, it will enter in that region, right? It will cross that Lakshman Rekha and it will never come back. It got it. So that is what it is happening here. That is the concept. Clear what I talked to you? Is it clear? Any doubt in that, Arushi?
So if it goes the closest distances? I didn't understand that part.
Okay, I'll tell you. This pink one is the path for the alpha particle. Once it is going close, 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 close to the nucleus, nucleus is having all positive charge. So all the time it is repelling it, right? All the time it is repelling it. So it will be slowed down, slowed down, slowed down, and it has to stop somewhere. Yes or no? Now let us
Yes.
understand a step by step. It is stopping somewhere. Now that stop can be anywhere. Suppose this particle, alpha particle, has started here, gone, and that velocity is not sufficient, then it may go up to that and then come back. Right? Clear? Right?
Yes.
Now I'm increasing the velocity. What I'm doing? I'm increasing the velocity. This velocity I'm increasing. What will happen? This alpha particle, now it was coming back from here. It will go more closer next time. How much closer it can go to the nucleus? That is the point. Nucleus, inside the nucleus, there is a nuclear force. Their law is altogether different. Outside that, okay, Coulomb's law is being followed. Two positive charge, if you keep it, they are going to repel each other. That we know. Correct. So under that, the alpha particle was slowed down, and stopped somewhere before going back. Now we kept on increasing the velocity. So that alpha particle kept on coming closer, closer, closer to the nucleus. But how long close it can go? The moment they cross this, you are seeing that this size of the nucleus I have taken with the help of this line. Got it? Right? This is the size of the nucleus. Is it clear what I said?
Yes, sir.
Right? So if it is inside, if velocity is more, an alpha particle you are able to push into that nucleus. Once it is inside the nucleus, the rule is different. The rule is governed by nuclear forces. Nuclear forces are always attractive. So this alpha particle, okay, it is positive. Your nucleus is also positive. There are proton inside, positive charges, but is not going to repel once it enters in this within that region. Got it? It will be undergo, it will experience a it will experience what? It will experience a nuclear force which is attractive in nature. So it will be trapped inside. Got it? Got it? And you can understand this way. Every nucleus is having proton inside, that right? And it is not just one or two protons. It all depends on what kind of material we are having. Come out of it. They should come out of it. Coulomb's law, if you think on the line of Coulomb's law, that they are not doing. Because there is nuclear forces inside the nucleus it acts, which is attractive in nature. So they just attract each other in place of, even if they are positive. So once alpha particle being positive, fine, but once they enter in that region of the nucleus, you will find that it will never come back. It cannot come back and retrace back its path. Got it? So I'm looking for that velocity where it is just able to come back, right? Beyond that, if I'm increasing the alpha particle initial velocity v, I'll find that it will enter in that. It will enter in the nucleus. Is it clear now? Very clear. No
So,
doubt
so
in that?
basically, it's the closest distance it can go without going inside the nucleus.
Yeah, exactly. Closest distance means it can go that much close. It cannot go beyond that, because if it is going beyond that, it will be trapped. It cannot come back. Are you getting?
Yes,
Clear?
sir.
So that also determines, with this help, we can determine the size of the nucleus also. How come? We'll see that. Right? So I'm taking, this is the point where the velocity will be 0, because it has to come back. Got it? So from this velocity, initial velocity is equal to v, to the final velocity is 0, there is a loss in kinetic energy. Am I right? Conservation of energy is very much there. So this loss in kinetic energy, where it is going? It is going as gain in potential energy. Got it? Gain in potential energy. And we can find easily that, right? So now we are going to see this closest distance from the center of the nucleus, call this as R naught. It is known as R naught, denoted by R naught, right? Now, as we have discussed, that loss in kinetic energy from where to where, from a start point, I can say O to the point here A, right? And this is, I can say C, that is your, C is your center of nucleus, right? A is the point up to maximum, up to that it can go. So R naught will be what? C to A, the radius of this nucleus. Yes or no? C to A, which is nothing but the radius of nucleus. The things are becoming clear to you now. So loss in Ke from your where to where, from O to A, will be gain in Pe for the same O to A. Can you make it out now? Loss in Ke means half, yes, m of the alpha particle. Am I right? Half m, and then v square minus half m, 0 square. At A it will be 0, velocity will be 0, and then gain in potential energy. Do you know the potential energy of the between the two charges? Are you aware of that? Potential energy. This is your electric potential energy. In electrostatics part, you must have seen this. This is your, do you remember? 1 by 4 pi epsilon naught. Yeah. Q1, Q2 divided by R12. That is the potential energy, electric potential energy. So once the particle is at A, say even it is at a few meter, even if it is say 1 meter, I'm taking 1 meter is too big in front of the distance C to A. Yes or no? It's all we are comparing. Means if you say Bangalore to Banipal distance is, say I'm telling okay 370 kilometer, and this 370 kilometer I'm just discussing in front of the distance of Earth from the sun. So this is just nothing, right? So for me, I'll say that the distance of sun from the Earth is infinite, right? For us, it will be infinite. Same way, C to A is very small, in the order of 10 to power minus 14, we had seen earlier. So distance of C to O will be infinite. We can take it infinite, right? So I'll be writing gain in potential energy where it will be more. Wherever that R12 in the formula is less, we'll find it is more. And R12 is the infinite, it will be 0, of course. So, well, I can write this as your P at A is more minus P at O. Yes or no? So P at A, what it should be? P at A, can you make it out? 1 by 4 pi epsilon naught Q1, Q2. What is the Q1? Is alpha particle, correct? So I'll be taking Q1 alpha particle is 2e and plus 2e, of course. And then other one is that of the foil, whatever, metal foil. So I'm taking this as Z into E. They are the charges Q1, Q2 divided by the distance between them. So distance is C to A, alpha particle at this point I am considering, right? This same alpha particle has come here. So yes, the distance between C to A has to be taken. So this is your R naught. As far as P at O is concerned, this is your 1 by 4 pi epsilon naught 2E and then it is your ZE, correct? And divided by infinity. If it is infinity, 1 by infinity is 0, correct? So this in turn, it will be your 0. If it is 0, I'm going to have this fellow as 1 by 4 pi epsilon naught 2e into ZE by RO, correct? Can we write like this? Yes, got it. So we can get the value of your thing. Now here, if you want to write the velocity, means anything we can find. Normally, this fellow is your Ke. This fellow is your Ke, correct? Ke at O, initial Ke, right? So call this as say K. K is your initial Ke. Initial Ke of the alpha particle. Right. So K I've taken, therefore K will be this much. I'm interested to get my RO. So RO is equal to K. I'll take on the other side. So 1 by 4 pi epsilon naught. And then here it is 2. And then Z. Mind it, 2 and Z looks like similar. So you have to take care. A square and divided by, what is that? K. Right. So this is the expression. You get it for the closest distance. Now,